grounding clause, specifically National Electrical Code Section 410.18a, addresses the protection of unqualified personnel from electrical shocks. It mandates that exposed metal parts, such as bracket-supporting exterior fixtures, be grounded or insulated from ground and other conducting surfaces, or be inaccessible to unqualified personnel. Some inspectors hold the belief that bracket-supporting exterior fixtures must be grounded irrespective of whether the fixtures themselves are grounded. The rationale is that the bracket could become energized if the fixture becomes loose or damaged. However, a different interpretation exists, centering on the specific wording of Section 410.18a. The clause explicitly states that lamp tie wires, mounting screws, clips, and decorative bands on glass spaced at least 38 mm or 1 and 1/2 inches from lamp terminals shall not be required to be grounded. The crucial point of contention lies in whether the brackets in question are analogous to mounting screws. If the brackets serve the primary function of holding the fixtures in place and are spaced more than 38 mm or 1 and 1/2 inches from the lamp terminals, then, based on a reasonable interpretation of the code, the brackets do not necessarily need to be grounded if the fixtures themselves are already grounded. The key is understanding the intent and literal interpretation of the grounding clause. It is essential to prevent electrical shock hazards. Section 410.18 offers specific guidance, but its application can sometimes be open to interpretation, leading to differing viewpoints among electrical inspectors and contractors. Let's analyze the scenario with a more technical approach. Firstly, the purpose of grounding is to provide a low impedance path for fault current to return to the source, enabling overcurrent protective devices, such as circuit breakers, to trip and clear the fault. Secondly, if the fixture itself is properly grounded, any fault current should flow through the fixture's grounding conductor, not through the bracket. Thirdly, grounding the bracket might create a parallel path for fault current, which could be problematic if the bracket is not adequately sized to handle the fault current. Fourthly, the code makes exceptions for certain metal parts that are not required to be grounded, as mentioned earlier. Fifthly, it's important to consider the specific construction and insulation of the bracket. If the bracket is in direct contact with a grounded surface, such as a metal junction box, it might be considered effectively grounded. Sixthly, the use of sheetrock screws to attach the pancake box to the OSB is a separate issue. Sheetrock screws are not designed for structural support and may not provide a reliable mechanical connection. It is recommended to use appropriate fasteners that are designed for the application. Seventhly, the size of the pancake box, 3.5 cubic inches, might be insufficient for the wiring connections. The box fill requirements of the National Electrical Code must be followed to ensure that there is enough space for the conductors and devices. Eighthly, it is always best practice to consult with the local authority having jurisdiction, or OJ, to get their interpretation of the code. The AHA has the final say in how the code is enforced. Ninthly, proper documentation of the installation is important, including photographs and detailed descriptions of the grounding methods. Tenthly, ongoing maintenance and inspection of the electrical system are necessary to ensure that it remains safe and compliant with the code. Now let's consider the electrical conductivity of the bracket material. Is it a good conductor of electricity, such as copper or aluminum, or is it a poor conductor, such as steel or iron? If the bracket is a poor conductor, it might not be an effective grounding path, even if it is connected to a grounding conductor. Also, what is the surface finish of the bracket? Is it painted or coated with the non-conductive material? If so, this could impede the flow of electricity and make it less effective as a grounding path. Furthermore, consider the size and opacity of the grounding conductor connected to the fixture. Is it properly sized to handle the fault current? The National Electrical Code provides tables to determine the appropriate size of grounding conductors based on the size of the overcurrent protective device. In addition, what is the condition of the grounding connections? Are they clean and tight? Loose or corroded connections can increase resistance and reduce the effectiveness of the grounding system. Also, consider the type of wiring method used. Is it metallic or non-metallic? If it is non-metallic, a separate grounding conductor must be run with the circuit conductors. Furthermore, what is the voltage of the circuit? Higher voltage circuits require more robust grounding systems. In addition, consider the location of the fixture. Is it in a wet or damp location? If so, additional precautions must be taken to protect against corrosion and ensure proper grounding. Also, what is the ambient temperature? High temperatures can increase resistance and reduce the effectiveness of the grounding system. Furthermore, consider the presence of any electromagnetic interference, or EMI. EMI can induce currents in the grounding system and create noise. In addition, what is the impedance of the grounding path? Low impedance is essential for effective grounding. Also, consider the presence of any ground loops. Ground loops can create circulating currents and cause noise. Furthermore, consider the use of surge protective devices, or SPDs. SPD can help protect against voltage surges and transients that can damage electrical equipment. In addition, what is the frequency of the electrical system? Most electrical systems in North America operate at 60 Hz. Also, consider the power quality of the electrical system. Poor power quality can cause equipment malfunction and damage. Furthermore, consider the use of isolation transformers. Isolation transformers can help isolate the electrical system from ground and reduce the risk of electric shock. In addition, what is the grounding electrode system? The grounding electrode system provides a connection to earth and helps stabilize the voltage of the electrical system. Also, consider the use of ground fault circuit interrupters, or GFCIs. GFCIs can help protect against electric shock by detecting ground faults and interrupting the circuit. Furthermore, consider the use of arc fault circuit interrupters, or ASIs. ASIs can help protect against fires caused by arcing faults. In addition, what is the labeling of the electrical equipment? All electrical equipment should be properly labeled with its voltage, amperage, and other relevant information. Also, consider the training and qualifications of the electrical personnel. Only qualified electrical personnel should perform electrical work. Furthermore, consider the use of personal protective equipment, or PPE. PPE can help protect against electric shock and other electrical hazards. In addition, what is the lockout-tagout procedure? The lockout-tagout procedure is used to ensure that electrical equipment is energized before being worked on. Also, consider the emergency procedures in case of an electrical accident. Emergency procedures should be clearly defined and communicated to all personnel. Furthermore, consider the regular inspection and maintenance of the electrical system. Regular inspection and maintenance can help identify and correct potential problems before they cause accidents or equipment failure. In addition to all of the above, the integrity of the grounding path is paramount. The grounding conductor must be continuous and unbroken from the fixture to the grounding electrode system. Any splices or connections must be made in an approved manner and must be accessible for inspection. Also, the grounding conductor must be protected from physical damage. If the grounding conductor is exposed to physical damage, it must be protected by conduit or other means. Furthermore, the grounding conductor must be identified. Grounding conductors are typically green in color or green with a yellow stripe. In addition to the color coding, the grounding conductor must be marked with the word ground or the symbol for ground. Also, the grounding conductor must be properly terminated. The termination must be made in an approved manner and must be suitable for the type of conductor being used. Furthermore, the termination must be protected from corrosion. If the termination is exposed to corrosion, it must be protected by a corrosion inhibitor. Let's consider a practical example. Suppose the exterior fixture is a wall-mounted light fixture. The bracket is attached to the wall with screws and the fixture is attached to the bracket with screws. The fixture is grounded by means of a grounding conductor that is connected to the building's grounding electrode system. The question is whether the bracket also needs to be grounded. If the bracket is made of metal and is in direct contact with the wall, it might be argued that the bracket is already grounded through the wall. However, this is not a reliable grounding path, as the wall might not be electrically continuous. Therefore, it is generally recommended to ground the bracket separately by means of a grounding conductor that is connected to the building's grounding electrode system. This will ensure that the bracket is properly grounded and that any fault current will flow through the grounding conductor, not through the wall. Now let's consider another practical example. Suppose the exterior fixture is a pole-mounted live fixture. The bracket is attached to the pole with bolts, and the fixture is attached to the bracket with bolts. The fixture is grounded by means of a grounding conductor that is connected to the building's grounding electrode system. The question is whether the bracket also needs to be grounded. If the pole is made of metal and is in direct contact with the earth, it might be argued that the pole is already grounded through the earth. However, this is not a reliable grounding path, as the earth might not be electrically continuous. Therefore, it is generally recommended to ground the bracket separately by means of a grounding conductor that is connected to the building's grounding electrode system. This will ensure that the bracket is properly grounded and that any fault current will flow through the grounding conductor, not through the earth. These examples illustrate the importance of understanding the principles of grounding and applying them to specific situations. The National Electrical Code provides guidance on grounding requirements, but it is up to the electrical professional to interpret and apply the code in a safe and effective manner. The key takeaway is that the interpretation of the code can be nuanced and may depend on the specific circumstances of the installation. Consulting with the AHA is always recommended to ensure compliance and safety.